Harmonic analysis. Harmonic analysis is the process of finding the constant term and first few cosine and sine terms of a Fourier series expansion of f of x numerically. See, this harmonic analysis is a part of a numerical technique. So it is one of the application of a numerical technique in Fourier series. So it is a numerical procedure which calculates the constant term, which is a naught by 2 in this case, and first few cosine and sine terms, I mean a1, b1, a2, b2, etc. of our Fourier series expansion. So numerically, so numerical answers will come. So here in case of harmonic analysis, the problem will be solved in two different cases. So it depends on the period of a given problem. So if a given data is a periodic function of period 2 pi, so this comes under case 1. If the given data is a function of an arbitrary period, say 2L, so it comes under case 2. So first let us discuss what do you mean by this case 1, how to find the Fourier series harmonic numerically by using harmonic analysis concept when it is a periodic function of period 2 pi. See here, the Fourier series expansion up to n number of harmonics, where n takes 1, 2, 3, etc., when the period is 2 pi, is given by the formula f of x is equal to a naught by 2 plus summation n is equal to 1 to infinity a n cos n x plus summation n is equal to 1 to infinity b n sin n x. So this is the Fourier series expansion of a function f of x whose period is 2 pi up to n number of harmonics. So here n can take either the value 1, 2, 3, etc. So where this a naught, a n, b n are the Fourier coefficients which are calculated by using a formula. So a naught is equal to, it is 2 by capital letter n into summation y. A n is 2 by capital letter n into summation y cos n x, and b n is 2 by capital letter n into summation y sin n x. So these are the expressions for a naught, a n and b n. So where this n represents the number of x values given here. Right. So this is the expression for Fourier series, and these are the Fourier coefficients of f of x whose period is 2 pi. Now, suppose your function f of x is a periodic function of period, say 2L, arbitrary period. Then the Fourier series of that function f of x whose period is 2L up to n number of harmonics is defined by the formula. See this, f of x is equal to, it is a naught by 2 plus sigma n is equal to 1 to infinity a n cos n theta plus sigma n is equal to 1 to infinity b n sin n theta. So where this a naught, a n, b n are the Fourier coefficients which are defined by the formula a naught is equal to 2 by capital letter n into summation y, a n is equal to 2 by capital letter n summation y into cos n theta, and b n is 2 by capital letter n into summation y into sin n theta. So where here this n represents number of x values given, and this parameter theta is nothing but it is pi x by L. So the value of theta is pi x by L. So now if you look at these two expressions closely, so the difference is if f of x is a periodic function of period 2 pi, here x will come. If it is a periodic function of period 2L, instead of x, we are going to write theta, where theta is given by pi x by L. So the expressions are almost same. So the difference come only in the variable x here in 2 pi period and theta in 2L period. But remember this expression, theta is pi x by L. So these are the two different cases we have in a set of problems related to harmonic analysis. So when you want to find a Fourier series numerically, so it depends on the period. If the period is 2 pi, let us use this case 1 procedure. If the problem is periodic function of period 2L, then we use this set of formulae. Right. So once we define the formulas of Fourier series and Fourier coefficient, let us discuss how to solve a problem. I mean, I'm going to discuss about the working rule to solve a problem of Fourier series now. I mean harmonic analysis method. So here, step 1. So given a set of values, that means the data they are going to give for an unknown function y is equal to f of x. First, we find its period. So here, this is most important step. So because this harmonic analysis, it depends on the period of a problem. If the period is 2 pi, you'll apply case 1 formulae. If the period is 2l, you'll apply case 2 formulae. So it is very important to know what is the period of a problem. So how to identify this period? So this period will be simply identified like this. If the values of x, so they are going to give x value and y value. So there will be two rows, x row, y row. So see the values of x. If the values of x are given in terms of degrees, like 30 degree, 60 degree, 90 degree, or maybe like 0, pi by 3, 2 pi by 3, 4 pi by 3, something like that, starts at first quadrant and ends at fourth quadrant. So it is almost a full cycle. Starting in the first quadrant, ending in the fourth quadrant means it may be less than or equal to 0, greater than or equal to 0, sorry, and less than or equal to 360. So it is a full cycle of 360 degree, I mean 2 pi. So 360 can be written as 2 into pi. So if the values of x are given in terms of degrees or in terms of something like radians, 0 pi by 3, 2 pi by 3 and all, it is a problem of 2 pi period. And suppose the values of x are given like 1, 2, 3, 4, 2, 4, 6, 8, 10, or a by 2, a by 3, t by 2, t by 3, t by 6. So something like that, then that problem is a 2L period problem. Right? So if x is given in terms of degree or radians, it is 2 pi period problem. So otherwise it is 2L period problem. So arbitrary values will be there like 1, 2, 3, 2, 4, 6, 8 up to 12 maximum, not more than 12. They are going to give only up to 12, or they may give some alphabet like a by 6, a by 3, t by 2, t by 3, like that. So first you decide the period of a problem based on this condition, whatever I told now. So after identifying a period, suppose if your given data is a periodic data of period 2 pi, if it is a periodic problem of period 2 pi, then we write the Fourier series of f of x in the form of equation 1. That means in case 1 you have written this, we have called it as equation 1. So we write the Fourier series of f of x in this form, up to required number of harmonics. They'll ask up to 2 harmonics, 3 harmonics, like that. So harmonics means n values. Up to 2 harmonics means n will take 2 values, 1 comma 2. Up to third harmonics means you will take n is 1 comma 2 comma 3, like that. Expand up to that. So up to required number of harmonics, we write the formula for f of x using equation 1, and then we construct a data table consisting the given values, that is x and y, and then based on the formulas of Fourier coefficients, we write what is y cos x value, y cos 2x, y sin x, y sin 2x. So just we prepare a data table consisting these quantities. So this depends on the problem. When I take a particular example, I show you how to construct a table. So once you construct a table, let us find the summation of these terms. What is summation y cos x, y cos 2x, and all these things. That is, here we have written summation y sin x, y cos 2x, and all. And finally, we have an expressions for a0, an, and bn, as in case 1. See this. Summation y is summation y cos nx. So n is 1 means y cos x, n is 2 means y cos 2x, like that, y sin x, y sin 2x, etc. will come. So substitute your summation values, whatever we got in step 2, in that Fourier coefficient formula, we get what is a0, an, and bn. That means a1, a2, a3, etc. like that. So once you get this Fourier coefficients, so substitute them in your Fourier series expansion, that is equation 1, you get the required Fourier series up to given number of harmonics. So this is the procedure of solving a problem of Fourier series using harmonic analysis concept. Suppose if the problem is a periodic function of period 2L, then what happens? It is again same procedure we follow, but instead of x, I'm going to use theta, where theta is pi x by L. And we use the formula of f of x given in equation 2 and the formula for a naught, a n, b n. As in case 2, we prepare a table, find the summation value, substitute here and simplify. You get the Fourier coefficients. Substitute back in equation 2, you get what is the Fourier series up to given number of harmonics. So this is the working rule to solve a problem in harmonic analysis. So it includes three major steps. The first step is identifying what is the period of a problem. The second step is construction of a table and finding the summation values, that is summation y cos x, y sin x, etc. Third step is substituting these summation values in the Fourier coefficient formula here, simplify and calculate, you get the Fourier coefficient. Substitute those Fourier coefficients in the given Fourier series expansion, you get the required answer. So this is how we can solve a problem on harmonic analysis, and this is a common procedure for all problems here, right? And in the annual examination, in the V2 examination, so 100% question will come from the harmonic analysis. It is very, very important. One question will come, and remember it is a numerical concept. So easily we can do it in the annual examination. Easy to get 6 or 7 mark in the annual exam, but your calculations must be proper here. Right? This is one of the most important topic of your Fourier series methods, harmonic analysis. Let us see how to solve a problem of Fourier series numerically by using this harmonic analysis technique. So I'm going to take some examples and I'm going to explain how to find a solution of Fourier series expansion of a given data using this harmonic analysis concept when the period is 2 pi and when the period is 2L. So we'll take up some problems on this now. Okay, so we'll start with first problem on the Fourier series harmonic analysis. So I'll take problem number 1. Find the Fourier series up to first harmonic for the data, I'll just take down the data, x in degrees and y values here. X values are 0, y is 2, then when x is 45, y is 3 by 2, then this is 90 means this is 1, 135, 1 by 2, 180 is 0, 225, it is 1 by 2, 270, it is 1, and 315, it is 3 by 2. So this is the given data here. So to find what is the Fourier series expansion for this data, which is numerical here, using harmonic analysis concept. So let us see how to find. So this is the data given. So according to the working procedure of the harmonic analysis, the first step is you have to identify what is the period of a problem. So already I said, if the x values are given in terms of degrees, it is a 2 pi period problem. Otherwise, I can go for 2L. And you can notice that it is 0 degree. That means it starts at 0 line and ends at 315. And 315 comes under 4th quadrant. So the range of x is like this. Actually, it will be identified like this. Here the range of x is 0 degree to 315 degree. That is, I can say like this, 0 less than or equal to x less than 2 pi. Correct now? So 0, it is equal to 0 because 0 is there. But 360 is not there. But 4th quadrant starts at 270 and ends at 360. 315 lies in between 270 and 360. So it comes under 4th quadrant. So the boundary of 4th quadrant is, lower boundary is 270, upper boundary was 360. So it is Less than 360 I'm writing, not equal, because 360 is not there. So it starts from 0, first quadrant, ends at fourth quadrant. It is a full cycle, 0 to 2 pi. So if I subtract here 2 pi minus 0, you get 2 pi, that is the period. That's how we can identify period actually. But anyway, we can identify like this also. The values of x are given in degrees like this. Starts from first quadrant, ends at fourth quadrant. So it is a periodic function of period 2 pi. So always you're going to get a data like this. It starts at first quadrant and ends at fourth quadrant. So that means the first value will be in between 0 and 90. The last value will be in between 270 and 360. Maybe equal or in between also. So starts at first quadrant, ends at fourth quadrant, means it is a periodic function of period 2 pi. Right? This is how you have to identify. So let us write like this. So here f of x is a periodic function, of period 2 pi. So we have identified its period, and this completes your first step. And once you identify the period, so you know what is the formula for Fourier series expansion, right? Whose period is 2 pi. We know that f of x, when the period is 2 pi, the formula for f of x, the Fourier series is, it is a naught by 2 plus summation n is equal to 1 to infinity an cos nx plus summation n is equal to 1 to infinity, it is dn sin nx. So this is the Fourier series expansion of a problem when the period is 2 pi. And here what we want. So actually in the problem they said, find the Fourier series up to first harmonic. So therefore the Fourier series, I'll write fs, the Fourier series up to first harmonic. See, first harmonic means the value of n will be equal to just 1 up to first harmonic. Harmonic means n value will be equal to 1. Second harmonic means n will be 1 comma 2, like that. So number of harmonics means the values of n. So up to first harmonic when n is 1, you just put n is equal to 1 in this, we get f of x is equal to, it is a naught by 2 plus, so n is 1 means, so just expand by n, putting n is equal to 1. If you put 1, so it is a1 cos 1 into x, that is cos x, plus b1 sin x, right? So it is b1 sin, right here. So it is b1 sin x. So let me call this as 1. So this is the Fourier series up to first harmonic for this problem. So if I ask 2 harmonics means n will be equal to 1 comma 2. So the formula is a naught by 2 plus a1 cos x plus n is 2 means a2 cos 2x. And similarly, n is 1 means b1 sin x, n is 2 means b2 sin 2x, like this. So just by giving the value of n, expand it. So this is the Fourier series up to first harmonic in which the unknowns are this a naught, a1 and b1. So if we calculate what is a naught, a1, b1 and substitute back, we will get what is the Fourier series of a problem here. So this is how we have to do. Now what are the formula for a naught, a1, b1? See, we know that the formula for a naught is, we have, so a naught formula, you know, it is 2 by cap letter n into summation y. And an formula is, it is 2 by cap letter n into summation y cos nx. So it is y cos nx. This is the formula for an. So here actually I want a1. So if I put n is equal to 1, so this becomes a1 is equal to 2 by cap letter n into, it is summation y cos x. The summation y cos x. So this implies a1 is equal to 2 by capital letter N into summation writing A1 equals 2 by capital letter N into summation y cos x. Right? When n is 1, so it is 2 by n summation y into cos 1 into x, cos x. So this is the formula for A1. Next, Bn. So the formula for Bn is, it is 2 by capital letter N into summation y sin nx, y sin nx. This implies B1 equals, put n is equal to 1, it is 2 by capital letter N, 2 by capital letter N into, this is summation y sin x, right? Put n is equal to 1, so I get B1 is equal to 2 by capital letter N summation y sin x. So this is the formula for Bn. So we have a formula for A0, A1 and B1, right? If we calculate your values of A0, A1, B1 using this formula, and if you substitute in equation 1, you get the Fourier series. But how to find? What is n here first? See here, capital letter N is nothing but the number of x values given. How many are given? So 1, 2, 3, 4, 5, 6, 7, 8. So the value of n is 8. Right? So we have written the Fourier series of the given number of harmonics. The formula of A0, A1, B1 are written. N value is identified. The next thing is you have to construct a relevant table for a data, and hence you have to find what is summation y cos x, y sin x, etc. So let us construct a data table now. So the relevant table for a given data is given by, so let us construct a data table for a problem. So here I'll just go to the next page. First, your table should contain the given values, that is x values and y values, right? X value, y value. Next, what we want, just look at this. See here, y is there. Okay, y column already we have written. See here, y cos x is there. Look at this formula, A1. This is what I want to calculate, y cos x. So I need the values of y cos x. Means I need a column consisting y cos x. Next, B1, if you observe, we have y sin x. Right? I want this. X, y, then y cos x, y sin x. Let us enter the values. So x values are given here. Let us enter in the table. So x values are, it is 0, next 45, then 90, 135, 180, 180, 225, 270, 350. And the corresponding y values are 2, 3 by 2, that is 1.5, 1, 1 by 2, 0, 1 by 2, 1, and 3 by 2. So these are the corresponding y values. Now y cos x. So you can do one thing, you can just type in the calculator x colon y cos x colon y sin x. So in your FX 991 MS or ES calculators, you just type this. X you type, you put colon y, then colon y cos x, then colon y sin x. You just type it like this. You just write on that here, x, this button, y, then y cos x, then y sin x. You type in this way. Then you press calculate button. Calculate button you press. It will ask you the value of x. Then press equal. It will ask you the value of y. Just give the values of x and y. So it will start giving the value of y cos x, y sin x. So straight away you can find. Just find out by using your calculator, by typing like this. Okay. So If we calculate like that, we get, I'll write the values. Y cos x values are, this is 2, 1.0606, then 0, then minus 0.3535, then 0, then again minus 0.3535, then 0, then 1.0606. And similarly, y sin x values are 0, 1.0606, 1, 0.3535, then again 0, minus 0.3535, minus 0.3535. Sorry, this is 3, okay, 3535, 0.3535. Then this is minus 1, and this is minus 1.0606, minus 1.0606. 06, guys. Minus 1.0606. This is not writing here. Minus 1.0606. Okay. So this is y cos x values and y sin x values. Just type in your calculator and find. Put your calculator in degrees. Type like this and press calculate button. It will ask you the value of x. You put x0, y is 2. It will give you y cos x, then y sin x. Go on pressing equal, you get this. Straight away you can find out. And once this table is prepared, you just find the summation values from the table. See, from the table, I can write what is the value of summation y, then summation y cos x, then summation y sin x, the values of these things. So what is summation y? It gives 8. The sum of all these things, you add it, summation y will come 8. Now add all these things, summation y cos x. So summation y cos x, if you add all those things, we get, it is 3.4142. 3.4142. 3.4142, guys. Sometimes it will not write. 3.414142. Okay, I'll write y cos x below this. I'll write below here. Summation y cos x equals, it is 3.4142, and summation y sin x equals, summation y sin x equals, it is 0. If you add all those things, if you add c plus minus, this gets cancelled, minus 1 plus 1 gets cancelled, this gets cancelled, y sin x was 0. Just add them, this summation y cos x, y sin. See, once you get these values, let us substitute these values in the formula of this a0, a1 and b1. So substituting, so therefore a0 equals, so you know the formula for a0 is 2 by n. N means 8 into summation y is 8. So this 8 gets cancelled. So get a0 is equal to 2. So this implies a0 by 2 equals. So 2 by 2, it is 1. So the value of a0 by 2 is 1. Next, a1. So a1 is 2 by n. N means 8 into summation y cos x. Y cos x is, it is 3.4142. 3.4142. If I simplify this, we get the value of a1, and a1 comes around, it is 0.8535. 0.8535. And b1, you know, it is 2 by 8 into summation y sin x, and you know y sin x was 0. So the value of b1 becomes 0, right? So we got the value of a naught by 2, a1 and b1. So substitute these values. Substitute these values in equation 1. I mean in this. So if I substituting 1, substituting a naught by 2, comma a1 and b1 in equation 1, we get f of x equals, first term was, see this, the first term was a naught by 2, and you know a naught by 2 is 1 year, so it is 1 plus, so the second term is, it is a1 cos x plus b1 sin x. Anyway, b1 0, this term will not come, so it is a1 cos x. So substitute a1 and write. So a1 is 0.8535, so it is 0.8535 into cos x. And next term was 0, just leave it. So this is our f of x we get, and this is the required Fourier series expansion. So this is how we can find the Fourier series expansion of a given problem. I mean the data given to you using the harmonic analysis procedure. This is a common procedure for all problems. The only thing is I may change the period of the problem and the number of harmonics. So in the second problem, I am going to explain how to find a Fourier series up to second harmonics. So this is how we can, so second harmonics means another 2 terms extra will come, and again in the table 2 more columns extra. So but the procedure is same. So you can apply this procedure to find the Fourier series of any problem in case of harmonic analysis. So now we should start the second problem on harmonic analysis. Just take to the problem. Obtain the Fourier series, I'll write FS, Fourier series up to second harmonics, for the data, write the values, x in degrees, y values. So x values are 45, then 90, 135, 180, 225, 270, 315, and then 360. And the corresponding y values are, it is 4, 3.8, 2.4, 2, minus 1.50, 2.8, 3.4. So this is the data given. So we have to find a Fourier series up to second harmonics for this. So let us apply the procedure, whatever we have already discussed and whatever the procedure we are using problem number 1. Only the difference is up to second harmonics we have to solve. Now the first thing is, as usual, you have to identify what is the period of a problem. And I said already, so this 45 is between 0 and 90, means it lies in the first quadrant, and 360 is nothing but the upper bound of the fourth quadrant. So the quantity varies from first quadrant to fourth quadrant. It is nothing but a full cycle, 0 to 2 pi. So once you are 0 to 2 pi, you know that the period is 2 pi. Or I can identify like this also. So the values of x are given in terms of degrees or radians. I can assume that the problem belongs to 2 pi period. Otherwise, I can assume that the problem belongs to 2L period. So since it is a degree values here, so I can identify the problem is periodic of period 2 pi. So we'll take a Fourier series whose period is 2 pi now. So we know that the Fourier series of f of x of period 2 pi is given by the formula is f of x equals, it is a naught by 2 plus sigma n is equal to 1 to infinity, it is an cos nx plus sigma n is equal to 1 to infinity bn sin nx So this is the expression for Fourier series of f of x whose period is 2pi. Now here what we want? So we want a Fourier series up to second harmonics. So let us rewrite this expression up to second harmonics now. So the Fourier series up to second harmonics. So you know second harmonics means n will take two values 1 comma 2. So n will take two values here 1 comma 2. So given by is given by. So let us expand this by putting n is equal to 1 and then n is equal to 2. So f of x equals, it is a naught by 2 plus, for the first term when I put n equals 1, it becomes a1 cos x plus, when n is 2, this term becomes a2 cos 2x. Similarly, so put n is equal to 1 here, this plus b1 sin x plus b2 sin 2x. So let us call this as equation 1. So it is plus sin 2x here. Okay. So this is the Fourier series up to second harmonics for a problem. I am just substituted n is equal to 1 first and then n is equal to 2. So here this a0, a1, a2, b1, b2 are the Fourier coefficients. So we have to find out that. Now to find the values of this a0, a1, a2 and all, so we have a formula. So you know a0 can be obtained by a formula 2 by cap letter n into summation y. So an, the formula is, it is 2 by cap letter n into summation y cos nx, y cos nx. Okay, so this is the formula for an. So it is, assume that this is cos. Now here I want a1, a2, put n is equal to 1. So this implies a1 equals, so it is 2 by cap letter n into summation y cos x, summation y. Yes, I'll write here. I'll write below this. That is not writing. So a1, this implies a1 equals 2 by cap letter n into summation y summation y, just a minute, summation y cos x. So a1 is summation y cos x, put n is equal to 1. Now a2, so a2 becomes, a2 equals, it is 2 by n summation, it is y cos 2x, right? So an is this formula, put n is equal to 1, you get a1, put n is equal to 2, you get a2. Now similarly I want b1, b2. So we have a formula bn. The formula for bn is 2 by cap letter n into summation y sin nx, y sin nx. This implies b1 equals, put n is equal to 1, it becomes 2 by cap letter n into summation y sin x, summation y sin x. And b2 equals, it is 2 by cap letter n into summation y sin 2x. So this is the formula of b1 and b2. So we got A0 formula, A1, A2, B1, B2. Now what else we want? So I want what is the value of capital N. And here capital N is equal to number of x values given. Just count 1, 2, 3, uh, 4, 5, 6, 7, 8. So there are 8 values here. So N is 8. So period is identified, 2 pi. So based on that, the Fourier series expression was written. I want up to second harmonics. So N is 1, comma 2. So we have expanded this up to second harmonics. And the formula for this A0, A1, A2, B1, B2 along with N value was written. So once it is ready, we can go to calculation of a table. So I'll write the relevant table for a data is. So the relevant table for a given data is given by I just constructed a data table now. So I'll go to next page. So first, your data table should contain the given values, that is x and y. So I'll write x here, y here. Then if you look at the formula, if you look at here, you have y cos x, y cos 2x, y sin x, y sin 2x. So we prepare a table consisting these quantities. So I'll write y cos x, y cos x here, then y cos 2x, then y sin x, then y sin 2x. So these are the different parameters present in the formula. Now let us enter the data. X values. It is 45, then 90, then 135, 180, then 225, 270, then 315, then 360. And the corresponding y values are 4, then 3.8, then 2.4, then 2, then minus 1.5, 0, 2.8, then 3.4. Now, as usual, as I told in the last problem, you can just type in your calculator x colon y cos x colon y cos 2x colon y sin x colon y sin 2x. Then press calculate button. It will ask you the value of x first. You give 45. Then press equal. It will ask you the value of y. You press 4. Press equal. So see, these values will come. Then 5 cos x will come. Then press equal y cos 2x. Press equal y sin x. So like this, these values will come. So row wise you can write. So just calculate these values. So here I have a calculated value. Directly I will write. So you make use of your calculators and find out that. So the first, y cos x. So I'll write y cos x column. So it is 2.8284. Next is 0. Next minus 1.6970. Next minus 2. Then 1.0606. Then 0. Then 1.9799. Then 3.4. So this is the y cos x column, y cos x values. Next I'll write y cos 2x. So y cos 2x values are 0, minus 3.8. Used calculator to find out these values. So 0, 2, 0, 0, then 0, then 3.4. So these are y cos 2x values. Then similarly y sin x. So y sin x values are 2.8284, then 3.8, then 1.6970, then 0, then 1.0606, 0, minus 1.9799, then 0. So these are the values of y sin x, and finally y sin 2x. So y sin 2x values are 4, then 0, minus 2.4, 0, minus 1.5, 0, minus 2.8, and 0. Right? So use calculator, keep it in degrees and calculate this. So once you get these values, the table is prepared, just find the summation values. I want these values, sum of this, all these things, except x. I want a summation of all these things here. Let us find out. First, add all these values, we get summation y. So it comes around 16.9. Next, if I add all these values, you get y cos x. So y cos x value sum is, it is 5.5719 y cos x. Now similarly y cos 2x. So if I add all these values now, so it comes around 1.6. Next, y sin x. So y sin x is, if I add all these things in calculators, it is 7.4062, 7.40660, this is 6. Just assume that it is 6. 7062, and y sin 2x, it is minus 2.7, minus 2.7 here. So these are the summation values. Just adding like this, we get the summation values. Now substitute the summation values in the formulas. It is A naught, A1, A2, B1, B2. So if you substitute here A naught first, so A naught, the formula is, it is 2 by n. N means 8 into summation y. Summation y is 16.9. 2 by n is 8. Summation y is this. This is y. So summation y is 16.9. If I simplify this, you get the value of A naught. So A naught comes around, it is 4.2215. So sorry, 225 this is. 225. So this gives A naught by 2 is equal to, just divide this by 2, divide by 2, divide by 2, it is 2.1125, 2.1125. So this is the value of A naught by 2, the first term of the Fourier series expansion. Now A1, the formula for A1 is, it is 2 by n, n is 8, into summation y cos x. And what is y cos x? It is 5.5719, substitute here, 5.5719. If I simplify this, we get the value of A1. So it comes around 1.393. So this is A1. Now A2. So A2 values again same, 2 by 8, summation y cos 2x, and y cos 2x is 1.6. 1.6. If I simplify this, you get 0.4. This is our A2. Now similarly, I write here B1. So B1 equals 2 by n is 8. 2 by this is B1 is equal to 2 by 8 into summation y sin x. So y sin x is 7.4062. So this is equal to B1 value is 1.8516. So this is our B1. And finally B2. So it is 2 by n is 8, summation y sin 2x, and y sin 2x is minus 2.7. So we get B2 equals, it is minus 0.675. Right? So if I substitute the summation values in this formula, A0, A1, A2, B1, B2, and simplify, we get the values of A0, and turn A0 by 2, A1, A2, B1, B2. Now substitute all these values of Fourier coefficients in this equation 1, we get, substituting in equation 1, we get f of x equals. So first term was A0 by 2, and you know A0 by 2 is 2.1125, plus next A1 cos x. So A1 is this 1.393 into cos x, plus A2 cos 2x. A2 is 0.4. 0.4 into cos 2x, plus next B1. B1 is 1.8516 into sin x, b1 sin x plus the last term b2. b2 is, it is minus 0.675 into sin 2x, minus 0.675 into sin 2x. So this is the Fourier series up to second harmonics for a problem here. So this is how we can find the Fourier series of a given number of harmonics for a up to given number of harmonics for a given data here. So this is a common procedure for all problems here. So up to one harmonic means just A1, B1 will come. Up to two harmonics means A1, B1, A2, B2 will come. So problem become little bit lengthy, that's all. So this is a unique procedure for all problems here. So this is how we can solve a problem on harmonic analysis.